Okay, good afternoon, everyone. I know you are all chemical or material experts, but my work are more from the macro-mechanical viewpoint, so hope you will not fall asleep. Okay, my name is Qiaoyun Xie, and my advisor, Dr. Wasso. We are from University of Pittsburgh, and the work I'm going to present today is about the dynamic fracture toughness of tantalum carbide and carbonate tubes reinforced silicon carbide ceramics prepared by spark plasma sintering. The motivation of designing this material is for aerospace and ballistic armors applications that to withstand oxidation, impact, and fracture. So the tantalum carbide was intended to improve the oxidation resistance, while the carbonate tubes were added to increase the impact and fracture toughness because of the high elastic modulus and high strength. But this work is more focused on the understanding of fracture toughness and possible toughening mechanism that with carbonate tubes. Investigators attempted to extend the static ASME standard into dynamic loading range, and the specimens were designed as 3-point or 4-point bending with pre-cracks in the beams, while the dynamic loading was applied with a split Hopkinson pressure bar or job weight tower or the Sharper tester. But up to now, there has not been a complete standard to measure and characterize the dynamic fracture toughness for the ceramics because of the difficulties in both the dynamic fracture theories and the experimental techniques. So in this work, we employ the vigorous indentation to measure the static toughness, SEM to directly observe the crack propagation, and the split Hopkinson pressure bar to measure the dynamic fracture toughness. So this table lists the detailed information about the powder properties. It is critical that the carbonate tubes should be distributed into the matrix uniformly. So first, the carbonate tubes were added into the ethanol solvent at a concentration of 1 weight percentage per volume, and then authenticated for 45 minutes. And subsequently, the matrix and reinforcements were added and then fully stirred by authentication for another 90 minutes. And in the last step, the suspension was baked for about 10 hours until complete dry and then crushed into the powder. So this SEM images showing the mixed powders and a higher magnification of the image showing the relative larger particles. And from these two pictures, we can see that the carbonate tubes were well distributed within the mixed powder. Spark plasma sintering is an innovative sintering technique that simultaneously application of pressure and electric field. So this is a heating furnace, and the vacuum chamber is a main part of the furnace. It consists of the electrodes, the graphite spacers, and the sintering molds. So the powder is placed in between the punch and dyer and held in between the electrodes. Under pressure and electrical field, the temperature quickly rises, which allows the sintering temperature 200 to 500 degrees C than the conventional sintering temperature and a much shorter sintering time. A two-stage sintering technique was developed to achieve the improved densification and mechanic properties. So in stage 1, heating rate of 130 3 degrees per minute was used for the first 9 minutes until the temperature increased to 1200 degrees C with a holding time of 3 minutes. And the pressure in stage 1 was 30 megapascal. And in stage 2, the pressure was increased to 90 megapascal and the temperature increased to 1800 degrees C with a holding time of 10 minutes. And after cooling down, the samples achieved a high relative densification, about 98.4%. So here's the whole process of the sample fabrication. So first, the powder matrix, reinforcements, and sintering aids were mixed homogeneously by ultrasonication, and the mixed powders were compacted into the sintering molds, and then these are the materials after sintering. So vigorous indentation was employed to study the static fracture toughness. These are the cracks generated by a square-based pyramid indenter. And this estimate standard was used for the fracture toughness for advanced ceramics, and the specimen was prepared according to the pre-cracked beam method with a straight-through crack created in the beam. The thickness of the crack is within 0.1 millimeter, and the normalized crack size is within this range. And the right figure, the outer span of the fixture has outer span such that 4 to 10 times of the beam height. And the dynamic fracture toughness was conducted using the split Hopkinson pressure bar to achieve the constant loading rate by the path shipper. It is glued onto the incident bar, and upon impact by the strike bar, the plastic deformation of the path shipper continuously increases its effective diameter, which allows increasing momentum transfer from the strike bar to the incident bar. And these are the theoretical backgrounds for the Hopkinson pressure bar. What we're interested for the dynamic fracture toughness are the strain rate, force, and energy absorption. As this experiment was designed in such a way that the fracture was deformed under dynamic equilibrium, so this dynamic fracture toughness could be evaluated by using the static expression, where the force is maximum dynamic force captured from the Hopkinson bar, and the second equation is the stress intensity factor coefficient as a function of the normalized crack size. And these are one of the pre-cracked samples and fractured after the dynamic impact. And these are the waves captured from the Hopkinson bar, the incident, reflected, and transmitted waves. So this constant slope of the incident wave conveyed that the loading was under constant loading, but the small transmitted wave is because of the mechanical impedance mismatch between the pre-cracked samples and the bars. The energy absorption increased as the crack propagated and then decreased when reaching the critical energy absorption, because at this time more energy was released than consumed by the crack growth. And the nearly constant slope of the force time curve confirmed again that the fracturing was under dynamic equilibrium. So the loading history could be evaluated by the stress intensity factor history near the crack tip. And the peak force was assumed as a fracture initiation point. As the impactor energy generates strain rate effect on the samples, which such as the strength and the stiffness. So the strain rate sensitivity was controlled for the fracturing study. So both the maximum energy absorption and maximum loading force increased with the strain rate. The maximum loading force was used to calculate the dynamic fracture toughness. So this established the static and the dynamic fracture toughness. Generally, the dynamic fracture toughness is higher than that of the static one because of different failure modes. As the increase of the strain rate to a certain range, the fracture toughness was very sensitive. So the dynamic fracture toughness should be evaluated in a relative low and stable range. So toughness mechanisms for fiber reinforced composites are fiber pull-out, interfacial debonding, crack bridging, and crack diffraction. So these are the cracks generated by the viscous indentation. The main crack initiated from the tip area and extending forward radially. Also observed are some secondary radial cracks which may have relieved some of the residual stress and decreased the crack opening. The surface floors often acted as stress concentrators which initiate the crack, but they may also slow down the cracks by relaxing the stress field near the crack tip. So the many toughness mechanisms observed are the crack diffraction and crack bridging. So the crack diffraction is the interaction between the cracks and the carbonate tubes, where the interface has a relatively lower toughness than that of the crack propagated through the reinforcements. But crack diffraction is a crack propagation perpendicular to the actual direction of carbonate tubes in such a way that carbonate tubes stretch freely along the cracking surface, which restrain the crack opening and reduce the driving force for crack propagation. They are consistent with the perpendicular cracks reach the interface and propagate it along the interface rather than cutting the grains. So in this work, we the tantalum carbide and carbonate tubes reinforced silicon carbide ceramics were successfully prepared by SPAC plasma sintering, and the dynamic fracture toughness by Speed Hopkinson Paribas was investigated based on the static Smith standard. And generally, the dynamic fracture toughness are higher than that of the static one because of different failure modes. So this composite exhibited a more strain rate dependent property for higher strain rates, and the toughness mechanisms of carbonate tubes, diffraction and bridging were direct observed, which restrain the cracked opening and go further under the loading. Thank you for attention.
Thank you very much.
Thank you.
Questions? Yes.
Just a couple of questions.
Yes.
Do you run any controls? And also, where the strain rate sensitive comes from? Because as far as I recall, carbides are not rate sensitive.
Do you mean why the higher strain rate generates the sense?
Just want to find out actually what is the element of the principle that makes all these composite behave strain rate sensitive.
I think every material has strain rate sensitivity because of the dynamic effect, because that will change the material properties such as strength and stiffness. But there's a certain range for different materials. I think for this material, we found out that at that certain strain rate, there's more strain rate dependent, so that would be not preferable for the real applications, I think.
Okay. Thank you once again.
Thank you.